Okay. So good morning, everybody. And I'm giving this talk when the LHC run 3 after a long gap has started. I'm supposed to cover results from ATLAS and CMS. This is not a talk on behalf of CMS and ATLAS. This is more my personal picks from what I think are some of the important and relatively new results from run 2. So run 2 of LHC has been an era of achievements and challenges. We had a integrated luminosity per experiment of about 140 femtobarn inverse, and this is the run 2 2018 line of luminosity compared to this for run 1. So 2012 8TV run collected 23.3 femtobarn inverse compared to 2018 of 68.2 femtobarn inverse. Now this large luminosity has come with challenges. Run 2 sees almost twice as much pileup events. In 2018, the mean was about 37 pileups, whereas for 2012, this was 21 pileups here, which also means serious bearings on the detectors. Here is one example of a detector component that I have worked with. This is laser light output from CMS electromagnetic calorimeter and at various eta. So this orange line is for the most forward eta, and it shows how the light output has degraded with increasing luminosity. However, with all of that, the experiments have been able to maintain stable and high performance. This is again level 1 plus HLT efficiency for isolated single muons over a wide PT range and for three different years of run 2. And one can see how stable the efficiency has been for the muons. This is another example from, this is a CMS electromagnetic calorimeter relative resolution of the calorimeter as a function of eta of the superclusters in the calorimeter. The black ones are 2012 resolution, and then the 3 colored ones are 3 different years of run 2. And it shows that in spite of the higher radiation environment, we have been able to maintain the resolution reasonably well. And this has needed a lot of efforts in calibration, and also many machine learning techniques have come into play during the run 2 period. That's the map of standard model in one slide as measured. This is from CMS. There are about 50 measurements in here, and which includes the WZ gamma cross-section measurements and electroweak production top and Higgs. All of that summarized is that the standard model rules, and deviations in these may need, will indicate new physics and may need effective field theory, but no such smoking gun as of yet at the end of run 2. So run 2 has been, in short, the measurements on Higgs and looking for anything beyond Higgs during this period. So a lot of the results that I will show will be on the Higgs sector. But before that, one interesting measurement on standard model, that's the top mass measurement. This one is again a CMS measurement where we measured both the, along with the direct mass measurement, a pole mass measurement was done. So this was done with 2016 data collected during run 2, and the direct mass was done using TT bar going to leptons plus jet. Pole mass was done in the same channel with one additional jet. For the direct mass measurement, full event kinematics was fit to the TT bar hypothesis, and then with constraints on the top quark mass, mass of W, and PT balance between the TT bar. And the maximum likelihood fit was performed to extract MT as a parameter. So all of this led to the most precise measurement so far of 171.77 GeV with a plus minus 380 MeV error. It's precise by 0.12 GeV with respect to the previous one. So this one is the muon channel MT fit, and that's the electrons plus jets channel MT fit shown in this diagram. And for the pole mass measurement, a fairly involved MVA analysis was done and trained to classify events into TT bar plus 0 jets and 1 jets and Drellians plus jets. The pole mass was extracted by a chi-square fit, and so here it's the differential cross section in the bins of the rho parameter, which is essentially the inverse of the invariant mass of the TT bar jet system, and the measured mass stands at 172.94 GeV with 1.37 GeV, 1.34 GeV error. So with that, let me move to the Higgs sector. This is where a lot of new results have come during run 2. About 30 times more data compared to the time of discovery was attained. I think Atlas saw 8 million recorded Higgs events during this period. So this is results from Atlas, Higgs production and decay rates. The SM so this is the top plot is the production rates for gluon fusion, vector boson fusion, and the associated productions. These ones, and this is TT bar H, and then TH, which is newer, shown in a different scale. These in the bottom panel is the ratio to standard model, measured to standard model ratio for the TH channel. It's at a different level of accuracy. So the scale, note that the scale is different here. In doing this, the SM branchings are assumed for production rate measurements, and for the branching measurements, the standard model cross sections are assumed. Systematic and statistical are comparable. They at this point, and they are smaller than theory errors. Experimental uncertainties are lowered by a factor of 2. These are the decay mode measurements. The new ones are Z gamma and mu mu. The rarer channels, these are also being measured or have been measured during run 2. So for WH, 5.8 sigma, for ZH, 5.5 sigma, and for TTH and plus TH, 6.4 sigma have been observed. So now about the mass and width measurement. This is a width measurement work from CMS. using off-shell Higgs boson production. And it's the first measurements of its width from the off-shell production. So in standard model, Higgs going to two vector bosons is about 10%. In about 10% cases is off-shell, and off-shell results can be interpreted in terms of on-shell. So in this CMS analysis, 2L, 2 nu decays, so H to ZZ to 2L, 2 nu is used along with, and it's combined with four lepton final states. So in this work, it relies on this, that on-shell sigma is proportional to the production signal strength parameter given by the squares of the production and decay couplings divided by the width of the Higgs, whereas the off-shell is proportional to mu production times the decay width. And this is, so from these two, one can extract the decay width of the Higgs. And essentially, this is the number of on-shell plus best fit is shown here. And from this, one extracts the Higgs width. That's the Higgs width in MeV, and the likelihood on the y-axis. The black line corresponds to combination of the 2L, 2 nu channel combined with the 4L. So 4L on shell plus the off shell, and then green is for 2L, 2 nu off shell and 4L on shell, and the purple is for 4 lepton off shell plus 4 lepton on shell. So in standard model, the Higgs width is 4.1 MeV for 125 GeV Higgs, and what has been observed is this. So we observe Higgs width of 3.2 plus 2.4 minus 1.7 MeV, and with this observation, mu off shell equals 0 has been excluded at 3.6 sigma. This all has good sensitivity to off shell VBF production. The major systematics in this analysis have come from NLO electroweak corrections on the ZZ background, gluon Higgs production plus 2-jet modeling, and gluon to ZZ background K factors. So now moving on to mass measurements. So this is a summary of mass measurement from CMS. I probably should have put the discovery time plot of this to give a contrast, but now one sees a very clean peak at around 125 GeV, and this is the summary. So this is run 1 Higgs to gamma gamma, and this is run 1 Higgs to ZZ to 4L. That's run 1 combined. Now this is 2016 Higgs to gamma gamma, and this is Higgs to ZZ to 4L. That's 2016 combined, and that's the run 1 plus 2016 combined. So one can compare this 0.14 plus minus 0.11 GeV for stat and systematics with the run 1 combined, which is which is twice. So we have gone down by a factor of 2 during the run 2. Then this is 15 minutes. Okay, so I have to move faster. This is from Atlas H2ZZ to 4L in run 1 and run 2. Again, this is the their real improvement came from improved PT scale uncertainty for muons. So this is the scale and resolution of muon. So over a wide PT range and over the range of eta in the detector. So the subparmil precision on dimuon mass scale and percent level precision on dimuon mass resolution, and the combined result error stands at 0.18 GeV. So that's the Atlas 4L mass distribution now with 139 femtobarn inverse. This is the mass distribution, and that's the fitted one. And the final measurement stands with a error of 0.17 GeV statistical and 0.03 GeV systematic. So so we're still statistics dominated, and in this the main systematic comes from the muon scale. Now we saw that Z gamma and dimuon rare processes have been observed. Here is one example of Higgs to dimuon measurement. I will have to skip a lot of details in the interest of time. In this case, a BDT analysis like the gamma and 4L, a BDT analysis was performed. This is the most sensitive probe to the Higgs coupling, and that's why it's also important. And it has a branching of 2.18 into 10 to the minus 4. It requires, so 2 well-isolated muons were required, and then a fit to the dimuon mass peak was done, which shows a little bump here. And the search was divided by production mode, for which a BDT discriminator was used. And then categories with different purity signal purity was chosen based on MVA discriminator score. But this is the final observation. So that's so from this the best fit mu value from the various production categories are here. And so these are the dark and light blue bands are the 1 sigma and the 2 sigma bands. The VBF gives a mu of 1.36 with the smallest error. That is the coupling strength kappa mu, the Higgs to muon coupling strength modifier extracted from this analysis, which has the best fit value slightly off of 1. I'll come back to this in a minute. And then Z gamma also has been observed. Z gamma production is a loop level process, and its branching fraction is about 0.69 of the Higgs to gamma. Again, a BDT based analysis has been done. The event samples have been categorized. So it's categorized in various production modes, and then within production modes, there are further categories made in terms of the BDT discriminating variable. And that's the observation of Z gamma. We observe a local significance of 2.7, whereas 1.2 is expected. The measured value of sigma pp to h and then branching to Z gamma stands at 0.21 plus minus 0.08 picobarns. So now with all of that, we have been, so now we are able to see all the couplings of the standard model Higgs. This is from Atlas. The fermion coupling versus vector boson coupling map from, so that's the Atlas measurement, and this is the standard model prediction. This is from CMS, the same plot. This one, the red cross is, and these 1 sigma, 2 sigma contours were at the time of discovery, whereas this is the standard model point of 1, 1, and that's the latest CMS observation with the black dotted line and black solid line showing the errors at the end of our run 2 analysis. So when does my thing end? Yeah, 3 minutes left. Well, so I have to really skip then a lot of results. So this is then the coupling strength parameters for both vector bosons and the fermions, which is supposed to scale with mass and mass square for the vector boson, and that shows the standard model beautifully. Dihiggs production has also been we have started seeing Dihiggs production. This is the present status of Dihiggs production. 4B channel being most sensitive. So the dashed line shows the expected 95% upper limit on the production. So the best one is from 4B, and then the weakest one is from BBZZ. And this is, we can look at the combined from 4B, BB tau tau, and BB gamma gamma, 95% upper limit on the sigma pp to HH. For 35, for early LHC run 2, that's where we are. And by HL LHC, this is what we expect to make an observation with this much precision. That's the prediction. That's CMS Dihiggs production limits on. So this is on kappa lambda, the self interaction, and this is the kappa 2V, the HHVV coupling. So the regions outside the shaded line are excluded. That's the theory line, and this is what is observed. I have run out of time just showing the Higgs results very quickly. Beyond Higgs, but the summary is known. There is nothing found beyond Higgs. So this fairly legible bar chart is from Atlas. It summarizes the non-observation of SUSY. Limits have been set to various superparticles, and these are the mass limits, like these ones for gluinos go up to 2 TeV. The summary is no evidence of SUSY found. I had one example from one recent analysis, which looks at various electroweak states. So this is BINO LSP, that's Higgs LSP, and we know LSP. This is done in heavy chi going to a light chi with WZ going to four quark modes. That's the summary. We exclude in this one, for instance, the charge mass is excluded for the BINO LSP scenario. It's excluded up to 1.11 TeV. So now, very quickly, also our wide range of dark matter searches in MET plus X channel also has not yielded any result. This one is from CMS monojet search. Let me go to the summary, and this has made this analysis looked at several interpretations. This one, for instance, is a vector mediator. So these are all in simplified models where we have a mediator going to chi bar, the dark matter pair, and this solid line. So this is contour of 95% exclusions. So 95% confidence level observed upper limit on log 10 of the signal strength is what is being shown here in mediator mass and dark matter mass plane. And that solid line is what has been observed. And we exclude a vector mediator at 1.95 TeV. And similarly for other models, this is for a scalar mediator, and there other mediators also have been observed. So I have to stop. Okay. So very quickly, one emphasis area has been long-lived particles. There are many signatures. Timing is so timing in the calorimeters is an important handle, and that has been used in some analysis already, which is exciting. For example, this is from CMS, that's the time resolution, and one has looked for HZ with the gravity nose, and this is the result is that we expect 0.3 and observe 0. So exclusions have been set. Let me skip. Yeah, so I'll stop with just last one where something has been seen in searches, and that's a tetraquark result from ATLAS. We'll see in the next talk a lot more of these. Tetraquarks, the 6.9 GeV was first seen by LHCb and in JPSI mode, and now ATLAS has also seen evidence of it. So let me skip all those and come to the outlook. So run 2 has been full of challenges with high pileup and high integrated luminosity, but performance has remained stable throughout. Thanks to robust reconstruction algorithms, many new recent results from CMS and ATLAS. So now new top mass measurements, Dighe results have come. Higgs to mu mu, Z gamma, these rare decays are observed. Tighter constraints on Higgs width measurement from off-shell Higgs, and then we have improved on mass and coupling measurements. So the list is long, and run 3 has started after a long gap, and we always have exciting time lying ahead. So thank you.
Thanks, Satyaki, for this. Indeed, it is very brave and courageous to cover CMS and ATLAS results in 30 minutes. So that constraint was there anyway. So questions? You. Yeah.
Yes.
Like, can we get some sort of quantitative understanding of how good this vertex, like how efficient this vertex reconstruction is compared to something like, let's say, a detector like Methuselah or Phaser, which is like very far away from the interaction point? And the reason I'm asking this, that these experiments, which are very far away, like which are built like for, displaced particles, although they have very good, they're supposed to have very good like reconstruction efficiency of displaced vertices, they are A, very far away, and B, they cover a very small region of your angular distribution. And since number one, like, I mean, particle decays happen like following an exponential distribution. So no matter how long the decay length is, a sizable portion will decay close to the um, like interaction point. So can CMS and Atlas, which have this like, advantage of covering a like almost 4 pi region, like sort of compete with these standalone detectors, which are built for like mostly, this one thing?
Okay, so somebody on, I mean, if someone here is on Methuselah detector, probably can comment better on the Methuselah. But what we can do in CMS is where the long-lived particle is actually that long-lived, so that it decays inside different parts of the CMS detector. And if it does, then there's a lot of studies going on now, and a lot of machine learning algorithms are being employed. We are designing new level 1 triggers to look at these. And with this, we can do a very good job of identifying displaced tracks, displaced decays within the calorimeters. Sorry, I'm not in a position to compare how this figures with respect to Methuselah. If anyone else has a comment, yeah.
Okay, so okay,
Sat.
Nishita, go ahead.
Yeah. Sorry, just to comment on the question that was asked. Was that Triparno, by the way? I mean, I could not see the face. Anyway, so you're right, of course, that there's a very small angular region that you are covering, and you are only looking at very far off distances. I think one advantage that these detectors might have is if you are looking for particles that appear primarily as missing energy in CMS. So you're right, there might be a small fraction that will still decay almost immediately. But from my experience, there's a lot of things that are going on already at Atlas and CMS. So there is usually a large background to most of the things that you can think of, including vertices and so on. So you need to have some very specific stringent conditions to make sure that your vertices are, first of all, from some new physics and not just from heavy flavor or something like this. And even then, yeah, it's not obvious. So if you have a specific scenario in mind, then maybe you can do a actual comparative analysis. In general, I don't think there is an easy answer to the question that you ask.
So one quick question from you.
Yeah. Sat.
Jan wanted to ask something.
All right, Satyaki, I have a question on your slide number 13. If you can go back to your slide number 13, then. When you fitted the kappa mu, I guess, from Higgs to mu plus mu minus decay. Yeah. Yeah, this one. Yeah, that one. So, see, I couldn't help but notice that the quoted value of best fit value of kappa mu is positive. Is that an inherent assumption? Because I cannot understand how LHC can be sensitive to the sign of kappa mu. Because if I let's say extend that likelihood plot to the negative value of kappa mu, I can presume that there will be another minima. Okay, and
So the kappa mu is essentially, so for standard model is supposed to be.
yeah, but that's a theorist bias, right? I mean, if you are, I mean, as we learned from the previous talks, that we should not just measure a subset of a theory and then extend our beliefs to the entire theory.
Yeah, that's well taken. But so you're saying that just from a free fit, I could have expected I could get a negative also.
You will definitely get, because it's not sensitive. I mean, you are not sensitive to sign of kappa mu, right? Because you are only measuring kappa mu square.
I'm measuring rate. That's right.
And actually, there are UV complete models that predict an opposite sign of kappa mu. Actually,
Maybe because of shortage of time, let us extend.
I do not have an. I mean, I don't know that if one goes to the negative side, then if there is another copy of.
All right, we can talk later then.
Yeah.
Fine, that's
Okay. Short question from Rohini and Judish, and then I think we have to go for.
Yes.
I would have expected GGA would have larger rates, and your errors are still pretty very much statistical, right?
Yes.
So why is VPF giving a more accurate?
No, so GGH is a larger rate, of course, but it eventually then it depends on how much.
But that's why I'm asking.
Yeah,
Asking actually.
how much background. I mean, the S over square root of B. The significance is not only from that, but yes, but the GGH also the error is fairly small. Maybe it's in fact. I mean, it's hard to tell from here. I have to look at the numbers. They are comparable.
For my eye, it looked like VPF was giving, and that
Yeah.
was surprising because at this stage one would have still expected.
Yeah, both are very comparable.
Judish,
Yep.
you have a question?
Thank you for for this very nice and informative talk. Just one thing that I didn't understand is the measurement of the Higgs width, because what you're doing is that you are modifying couplings in a uniform way, essentially like with a kappa formulation, which as we know makes no sense because it's not gauge invariant. So if you instead do it with effective operators, they will contain derivatives, meaning that the on-shell and off-shell couplings will be modified differently. So that measurement of the width is done under an assumption which is as strong as essentially assuming the standard model. And so what kind of test is that?
So your comment is that for the off-shell, this will get
right. For the off-shell, those G's that appear there are not necessarily equal to the G's that appear on shell.
Okay. Yeah. So that assumption, yes, indeed, has been made.
Right, but then you're not really testing anything beyond the standard model, really, no?
Yes, that essentially, that would essentially imply that standard model is assumed. So that's a criticism of this you have, or okay.
Okay, so let us thank Satyaki again for his brave effort to, within a very short time, summarize the results.